Hello, everyone. My name is Jacques. I have the pleasure of managing this game technologies team. I'm here today to start you off with the best practices for building spritekit games. So we're going to start this off with talking a little bit about the history of spritekit. It's now 1 year old. You guys have made thousands of games with spritekit, and I'm sure you've seen some of the successful ones out there, like 100 Balls, for example, even achieving the top one free spot. So what you guys have done with it is absolutely amazing, and we hope that some of the new features we've added are really going to help you make that next game. So let's go through what this talk is going to be about. We're going to discuss scalability best practices to help you save on cost as you develop your game and also set yourself up for the future. We're going to talk about game structure best practices, and then Nick is going to talk to you about performance best practices. So let me dive straight in to scalability best practices. So what I'm talking about here is setting yourself up so that you can add content to your game with the smallest possible cost, so that you can collaborate with the rest of your team and also perhaps work better for the future, learning better techniques. So one of the problems that you can see as a beginning game developer, and I used to be one of those, is you get really, really excited. And so you start on this idea that you have. And I mean, the idea is right. You want to get your game going as fast as possible. So you dive in, you hard code. Everything's done in one scene. All the art references are done in the one place in code. You hard code level 1. Level 2 was a bit more work to make it different. Level 3 looks the same because, face it, you just did copy and paste. And, well, you're probably stuck on level 4. You're thinking, different, it's going to take time. Probably going to do copy and paste again. The second problem is you tend to get tempted to write data as code. And here's just an example of something you could get stuck doing even in spritekit. I'm saying spritekit is excellent, and you probably won't get stuck with this, but you might get stuck with this in other APIs. You're encoding things like the position of your nodes inside code. You're encoding rotations. You're probably even encoding the number of objects you have in code. You may be encoding properties like how many hit points you get, what types of units there are, the colors in code. And what you end up with is that you made changing art assets meaning changing code, right? So now the artist and the coder both have to make a change at the same time. The only visual feedback you get is your build and run, right? Iteration time has been worsened. And you're forcing your designers to be programmers because they need to edit code to change the game design. On the second level here, you're also duplicating structural code. And code as data is not very efficient, right? There are better ways of describing data, namely data. And also it's hard to change collaboratively because you're probably doing these edits in the same M or MM file for all the changes. So your artist has changed an art asset. Well, that's an M file change. So in your version control system, it looks exactly the same as your game designer changing a parameter. So the solution. Well, you've got to separate game content from game logic, as Norman touched on earlier. You want to separate scene structure from assets. So structure of your scene might be different from the actual artwork delivered. And you want to separate data from code. And we also want to make sure you're visualizing as early as possible. Build and run is not the best system in the world to visualize what's done. So implementing solution consists of putting a game logic in my scene.m. I'm referencing that here because that's what you get in the template. You put your game structure inside the scenekit serialized file, this myscene.sks, and you put your scene assets in separate SKS files that you're referencing. And if you can do sidecar data, we have a fantastic format called plist, which is XML when you edit and binary when you deploy. So the tools that we provide for you to do this in Xcode 6 is we obviously have a spritekit template, both for Objective-C and Swift. The editor, as Norman showed earlier, lets you do visual feedback, visual editing. Feedback is immediate. And you can also simulate the physics live. We also have, and have had for a long time, the ability for you to edit plist files inside Xcode. And it's as simple as creating a plist file adding arrays, dictionaries to them, and then reading them back in your code is super simple. So I'm going to show you a demo of the spritekit template and how easy it is to get set up both the wrong way and the right way. Okay. So let me show you here my very rushed example of making a sort of topple over the towers game. So I made a little hammer throwing game here. I just throw them at totem and I get a score. I was really excited about making this, so I just threw everything inside the game scene. Okay? I'm sure none of you have ever seen this before. You see here I'm referencing arc right inside the scene file. I'm setting positions of things and changing the properties. So I got this going really quickly, and I'm not saying this is totally wrong for you to do. Whatever you do to make money and get success is great. I'm just going to provide an alternative. So this ran, did the job. That's great. However, you could structure this slightly differently. So here I have a scene which, first of all, let's make sure it operates in a similar fashion. Okay. Yep. So it does the same stuff. Seems to be the same game. What I've done here is I've used the spritekit template, which provides you a start of separating code and assets. And the key here you're going to see is right on this line here. Game scene, unarchived from file. Well, that seems kind of cool. What's actually happening? Well, the template here has set you up with some of these amazing APIs that we have, that we're already using from Foundation. It's called nskeyed unarchiver. This is how you load and save all data that's related to spritekit. So there's a super special piece of magic that we're doing in here. We're telling the keyed archiver to replace any instance of skseed with our own class. So this means that any skseed that you've made, you can make it automatically load one of your own scene files. So now we've tied logic together with assets, even though they were designed separately. Okay, now let's go into the actual game scene here. Notice the setup level 1 here is markedly smaller than it was in the previous example. So what's happening here? Well, we're using spritekit's powerful search features to enumerate through the content of the scene, and by agreeing upon node names and conventions with your artist, you can make it really easy to pull the logical elements out of the scene by name and hooking them up to code. And here, we have said there's a totem node, and we're going to attach children based on level 1. So let's go through the scene here. This is the basic structure of this first theme. It's a base, it's got a background, and it's got a little empty node here, which I've named totem. So in code, I'm going to load up the scene. I'm going to fetch the node called totem. At that node, I'm going to attach level 1. And level 1 looks like that. So I've separated out the structure of the theme, which is my game, with the contents of level 1, which is just a stack. And continuing this theme, when I do my game logic, I keep using names in order to evaluate whether or not an object is a totem. This means that your artist can add incidental objects that are not named totem, add them to the scene, and they don't affect the scoring of your game. So just a simple example of what you should do to separate out your game logic from your game assets. Okay, thanks. Okay, let's recap. So you saw the spritekit template. What we're doing is we're taking a scene file, which in this case is myscene.sks, and your basic code files, myscene.h, myscene.m, and we're separating out the logic from the assets. The key here is to use nskeyed unarchiver, which some of you might not be familiar with already. You insert the class replacement in this case arc set class myscene.class for class name skScene. This replaces any reference to skScene inside the scene file with your own class. And it's as simple as that. So let's go into game structure best practices that you've seen an example. Motivation here is, of course, get your game running on the first day. How are you going to know that your game is fun if you're not playing it? So get it up and going on the first day. You want to do this without compromising on scalability, okay? Don't rush into it. And set yourself up to iterate collaboratively. Designers want to be designers, artists want to be the artists, coders want to be all of the above. So, make your generic level, as I showed in the example. Just make it simple. Get your designer to commit to where the general gameplay is going to happen, what object is interacting with what. Add placeholder content. I'll go through that shortly. Hook up interactions. So this is you as a coder and the designer working out what interactions are meant to be there. Get the game logic working, and then, of course, the easiest part of all, just finish the game. All right, so make your generic level. This should be logical layout only. So if you don't have any artwork right now, don't worry about it. Place markers where you think content is meant to go. So if you have action going from left to right, well, structure your scene that way. Place markers where you think the hero is going to begin. Name that marker hero. Place markers where you think enemies are going to start out in your scene. Probably name them enemy. And any logical layers you have, such as platforms, or maybe the background. You want to make sure you're not putting anything accidentally on the background. Then you move on. You add placeholder content. This is often what we call red boxing. So pick a color that you like for your heroes. Blue, perhaps, is perfect. Add them as colored sprite nodes. Don't bother with the texture right now. Just put them in the right spot, right size. And this is a key to your artist, that you're saying, I want this to be roughly the size over here, right? Because your artist can go and make crazy assets. Okay, now, make parent-child relationships here too. So particle emission locations, if you're making a train game, it is highly likely that smoke is going to come out of the smokestack, and that smoke should probably move with the train. So I've set that up as a parent-child relationship. Next up, hook up the interactions. So this is the pass where you're going through the physics interactions and making sure that they're right. So for example, are objects meant to topple over? Are objects meant to stay absolutely put when they're hit by the hammer, for example? Sort out your collision masks, which objects are meant to interact with which, and make sure that you simulate this right with the next code. Get it right from the start. Then you get the game logic working. And this is where you initialize your scene logic and game logic together. So you're using those names that you set up in the scene, and you're hooking them up to search code within your actual game code. And we had a placeholder inside the sample before, which was a totem, where we loaded a level scene and replaced it wherever the totem empty locator was. This is where you want to do that. So here's a sample of me having the scene structure file on one side and the actual scene code on the right. And I'm just making sure that my code matches what I think the scene structure is. So, of course, just hooking it up is probably not going to make your game great and fun. You've got to make sure that it's doing what it's meant to be doing, and that you've got unit stats loaded, scores, and similar things. And there are two logical places within your scene to do this. There's one which is on first load, which is called init with coder. And this is going to get called automatically by the keydown archiver. The second one is did move to view, and this is when you're presenting it as a scene on your SK view. So let's jump into the details of that. So on first load, as I said, automatically called by NS keydown archiver. And this is where you load any sidecar data. Sound, for example, AI, or any unit stats that aren't going to change. It's called init with coder. Make sure you go super init or init with coder, depending upon what your superclass needs. And load up the enemy stats here. I just loaded it as an array from a plist. Very simple, just a one-liner. Next up, you can move to your onFirstShown initialization point. So this is called when skview present scene is called with your scene. And this is a great place to cache your visual elements. So SKScene is going to get loaded by the Keynote archiver, and all the visual elements, the PNGs that are referenced in there, are going to get loaded well before you get to here. So you can actually do quite a bit of work inside the move to view without worrying about a lot of loading costs and latencies. If you have a lot of visual elements you're going to interact with, cache them right here. In this case, I'm finding all the enemies, and I'm saving them away in my enemy array. So the motivation for doing this is that you want to have a simple way of taking your logical scene elements and hooking them up to your code. There are two different methods for searching. Child node named for finding a single element, and enumerate child nodes with name for multiple elements, and cache the results. I really can't stress that enough. You saw in the previous slide just a quick hint of a search syntax that might not have been apparent to you at first. We have an XPath style search in your scene, which in this case was / enemy. What that means is find all enemies from the root recursively down. Some examples here. Hero would just find a child called hero without recursing. / hero would find all the nodes named hero in a recursive order. We can also search by class, not just name, but class. So you can go / emitter node, would find all the emitter nodes in your scene. And you can also use glob-style partial matches, such as the wildcard here, where it's anything, any node named starting with he. Super powerful, and this is going to be your best way of hooking up your logical scene with the actual game code. And obviously that's what we did. In the sample that you saw before, you can see child node with name being used extensively to find the actual objects within the scene inside the game code. This is very fast, so you can do it often, but we do recommend you cache results if it becomes a performance problem. All right, last step, I'm just going to gloss over this one because it's easy. So, finish the game. That's totally up to you, of course. Add the artwork. You can then replace the textures on your red boxes, because hopefully your artist has delivered them at the right size. Add the levels that you need, which should be easy if you followed all the points. Add any effects. Norman showed you how easy it is to add shaders to things. You can also use core image filters on your effect nodes to add that special image post-processing effects. And then, of course, play, test, iterate. I can't stress this enough. And have fun. This is what games is all about. Make sure you're having fun when you're making your game. Okay, let me hand you over to Nick now to talk about performance best practices. Thank you so much. Thanks.
Oh, thanks, Jacques. Today, I want to talk about my two favorite things. Well, two of my favorite things. One, which is improving performance in order to squeeze down the amount of time that your game takes to execute 60 times a second, and then increasing the awesome that you can squeeze into that space that you made by improving your performance. So I have a bunch of topics to go through. Just to quickly give you a preview, we're going to talk about understanding what is involved in drawing and where the time is going to go. I'm going to talk about actions and constraints, how they're the secret window into the underlying spritekit engine. Physics, there's a cost hierarchy there, which is very helpful to understand. Similarly for shape nodes. Talk a little bit about effects and some good-to-know facts about our lighting systems. So, drawing performance. There's two things that impact your drawing performance in a big, big way. One is the choice of draw order, how it is that you submit your sprites to the engine. And two is sharing the resources that are used to accomplish that drawing. Now, spritekit has, by default, a sibling order draw rule, which implements the standard painter's algorithm. There's two rules. the parent draws first, then it recurses down and draws the children, and then their children, and so on as it goes. And children are rendered in the order that they appear in the child array. Now, in this diagram here, obviously the helicopter has got at its very bottom some missiles, then the body and the rotors, and it's straightforward to create this in code just by adding the various parts. Now, this is very convenient for prototyping, but what does it do to drawing performance? So here's my amazing game scene, and it's going to have a bunch of helicopters in it. Each piece, as we recurse down the draw order, comes in one at a time with a little draw call, and that's a lot of individual draw calls. It's going to take some time, and you get the idea. I just filled them all in there. Now, what spritekit gives you in order to avoid this problem is the magical third dimension. So let's have a look at what we can do with that. If we set ignore sibling order to yes, we can use depth to control the order. That's going to be pretty helpful. So we've got the helicopter. We are going to arbitrarily set it on level 100. Let's stretch out the rotors and pull them towards the camera at level 1. Now, let's push the missiles back, like that. So now they're stacked. Now, spritekit knows what you intended with your composite. It's not based on the order it was added in code or anything like that. It's based on something absolute, which is where is my parent in space. So what does that do for our drawing? Well, bit by bit, you can see that we've got a lot less draw calls because we're done already. So that's great. And you've got a whole bunch of performance back right away, especially if you have lots of objects. But you can go further, of course. Use texture atlases. So here, I've put all of the sprites onto one texture, and how's that going to help me? Well, here's my magical scene again with lots of helicopters, and boom, I'm done. Spritekit can know that's one texture. It knows what order all the bits have to be drawn in. You can just batch it all up for the GPU and blast it on out, potentially with one single call. So that's pretty awesome. Now, there's a whole bunch of other things that can be shared, and you should be aware of those things. We have a new normal map generation scheme, and you can see that there with my little flower block. Because spritekit textures are keyed off a name, and normal maps were generated on the fly and without a name and just assigned somewhere, if you're going to use that normal map on the block, you need to let the engine know that it's genuinely a shared thing. So generate your normal map, store it on a texture, and then assign that texture all the sprites that are going to use it, as opposed to every time you have that block asking for it to be generated. Similarly, we've got some cool procedural noise, which you might be like to use in your shaders or to provide some sort of television snow effect or something like that. If you can reuse the noise at the scale that you've generated, cache that off, because every noise texture that you make is going to consume memory. And once again, spritekit won't know unless if you tell it by sharing a variable in a cache pointer somewhere that it is actually the same texture. It won't know, and you won't be able to batch. A couple of other similar points. If you reference shaders from files, spritekit will know that vortex.fsh is vortex.fsh everywhere you reference it. So when you're prototyping, it's often very convenient to reference shaders from strings. So go ahead and do that during prototyping. But spritekit doesn't really have any way of knowing that genuinely these two shaders are the same, even though the source code might be the same. If you reference it from a file, then we can do all kinds of pre-analysis beforehand, just cache it all off, and it's going to go that much faster, because if all those helicopters have the same shader, once again, it knows it can just blast them all off like that. And then finally, a slightly esoteric point on batching here is we offer a number of blend modes, such as additive or multiplicative or whatever. Because changing a blend mode changes the GPU state, we have to actually interrupt the drawing every time you change that state in order to allow the bind to occur. So a trick you can use, you can imagine, for example, if you had some sort of a misty forest scene with a layer of trees and then a layer of creatures and then another layer of trees, and the trees have alpha in them. if you put all those things on the same Z, like literally exactly the same Z, then spritekit will know these things go together with their blend mode. And for example, all of the trees in the front can go out in one draw call with one blend mode. And that may or may not be just that little extra bit that you needed to get a little more time to squeeze in that little more awesome. Now, there's tools to help you evaluate graphics performance. So you don't just need to have like a mysterious mental model of these things. There's actual, quantitative things you can do to get some insight into what spritekit is doing behind the scenes. So first of all, there's a number of flags on the view which you can turn on and off in order to get some insight. There's the obvious frame counter, FPS, frames per second. There's a draw count, which is actually going to tell you how many batches did I get. There's your node count, which is how many SK, like spritekit nodes, actually went down the pipeline. And finally, the quad count. If you're using something like a shape, it might be comprised of multiple sub-quads. So it's going to tell you that. And I have just a quick little thing here to show you that. I have all these gears. It's showing 12 nodes. You'd have to inspect my scene graph to discover why there's 12. But there's 6 gears. You can probably guess sort of what might be going on there. It's a heck of a lot of quads, like really a lot. I have 12 draws, but it's running at 60 frames a second, so I'm pretty happy with that right now for my magical gear game. So the other thing you've got is the GL frame debugger. So there's all kinds of cool gauges tell you what proportion of this and that is happening throughout your frame. And it'll give you some insight into what GL calls are being invoked on the fly. There's a heck of a lot of documentation and information about this. It's a really fantastic tool for understanding the runtime characteristics of your game. You'll notice as you run this thing what's going on in the hardware corresponding to what's going on in your game, and study that. It'll give you good insight into what the engine is doing for you. So to kind of roll that all up, the idea here is pose your scenes as layers. Common Z values are going to help you a lot for the reasons I mentioned. Put overlapping things in different layers in order to control the draw order instead of using the sibling order. Sibling order, yes. Share your stuff. Blend modes go together. And use the HUDs and profilers to really understand what the engine is doing. All right, next up. Actions and constraints. As I mentioned in the introduction, the cool thing about actions is they really are a magic window into the very guts of the spritekit execution engine. Deep down inside, we continuously improve the performance of the various operations the spritekit provides. Actions are these little Objective-C things that you might think, that might be heavy, but it's not. It really queues up instructions for the execution engine, just a couple of bytes here and there to tell you what's going to happen. And then it puts it off into our internal queues and whatnot to run. So make an action. Here, I've got a node, and I'm going to rotate by pi, apparently, for 1 second. You can chain them, group them, reuse them. Here, my little airplanes that you might all be familiar with. They're rotating continuously for a period of a second. They're moving around and they're scaling. It's really simple to set this stuff up. The execution engine is ticking it over. It's almost free. It's great to let the spritekit engine do this stuff for you rather than coding it all up in your update. So a little bit about sequencing. Say I've got something that I have got waiting off stage left, like the secret monster who will make his appearance in less than 1 second. I can have it wait and then move. So that's like a sequence. Also, when my monster comes, he might rotate and scale and then fade away because he was merely a ghost. So that's the use of like an SK action group. And then you can compose those things as deeply and complexively as you like. Am I allowed to make up words? All right, so In this case, my monster is going to move, he's going to scale and rotate, and then he's going to fade away. Now, skaction.h is your friend, as is the documentation here. I'd like you all to carefully write these all down. No, actually go look at the documentation because there's a lot of it. Now, there's a ton of power in there. It's a lot of fun to play with. Constraints, if you're here for the previous section, Norman introduced quite well. I have just got a quick little summary slide here. Constraints are another thing which gives you access to the high-performance engine running underneath spritekit. In this case, it's running inverse kinematics. This little scene was set up in Xcode very quickly, just clicking and setting a couple of parameters. Here's another one that's actually new and cool. You can create a follow path node, which just takes a CG path rough. And if you've ever spent any time with Bezier splines and whatnot, the math is kind of hairy, especially making things move at a uniform speed is particularly hairy. So we've went ahead and given you an SK action to follow a path along a spline that you create. It's a Catmull ROM spline if you care. And we'll move things along it at a constant velocity for you. Click. There we go. All right. Orient to node, similar sort of thing. You don't need to bother with, arctangents and all that sort of thing. The blue ball is moving around. The arrow is following it. And the other really cool thing about actions is they're kind of latent in memory when you create them. Build them once. Take advantage of the fact that they're copy on add and that they run when you add it to a scene. My example here is that you might have a spaceship or a monster that's going to enter from stage left in the same way every time and maybe follow a path and then leave. If you create that node with the spaceship and the action, cache it on a pointer, and then copy it and add it to your scene, it'll run every single time exactly the same way, very, very little overhead. And another fun thing that's easy to overlook is the purpose of naming your actions. So in this example here, what I've got is the idea that I have a sprite that is basically going to do something like, say, follow a touch point. I might run an action that is like move to point. If I give it the name move, now I can override that action anytime I want just by using the same key. So it might be in progress. If I run the action again with a new point, it'll immediately segue without a hitch or stutter onto the new action and continue on. And finally, if my monster is coming in here and then he saw that I had, the big monster ray repeller 2000, and he decides he doesn't want to go all the way into the scene, we can just use remove action from key with his move key, and that'll cancel that action right away, and he can go and do something else, and we don't have to wait for the execution to play out to the end. All right. Next, physics. Physics are a lot of fun. I really, really love the new simulation tool that we've got in Xcode because the hardest thing about working with physics is getting the parameters right. Now, we've set things up with good defaults. For example, if you set a mass of 1 and a strength of 1 on a rigid body and a strength of 1 on a field, they're going to interact in kind of an interesting way out of the bat. But that's just a starting point for your iteration. So, rigid bodies, I just mentioned rigid bodies. That's all the things in your game. They're bouncing, falling, rolling, and sliding. The things that the physics engine has to do each frame are your rigid bodies, handling collisions and letting you know that they've occurred, and physics fields. Now, a primary thing for getting access to iteration and understanding what's going on is the new physics visualizer. So let's just go back to my gears game here. I'm dropping in these wonderful gears. And wait a second. His teeth weren't acting properly. What's up with that? The other ones are interlocking, but just not that one. So I'll turn on the visualizer, and you can see, oh, that one's a circle. I made a mistake somewhere, so I can go either in Xcode and click on my thing, or if it's procedural, I can look at my code, and I can find out, why did this one slip through the cracks? So this is your great first line of defense for just understanding what the dynamic behavior is if it's not what you expected. You can also use this mode for identifying quickly what is the cause of physics performance issues. An object might be stuck in a wall, and it might be an invisible wall because it was only there as a physics body. Now you'll just be able to see that, oh, it's continuously pushing in and out of collision and can't escape. And the next steps to solve that problem will probably occur to you. So, in order to take best advantage of physics, in order to get performance, so you can squeeze down the amount of time that you're spending, you can squeeze in more awesome, is to understand the cost hierarchy. First of all, dynamic objects cost more because their collisions need to be resolved and they need to be moved out of intersection than objects that are static, like hopefully the stage that I'm standing on. So if you can set an object to dynamic equals no, you're going to get a lot of performance back right away. At the most efficient end of the scale are circles. You can have dozens of circles for every other kind of shape that you can have, and circles might work really, really good for a lot of things, especially if they're circular or if they're small, so you're not going to really notice what the interaction is. The circle doesn't fit very well on that hammer. That's a bit better. The hammer, at least, has edges and stuff. This is more expensive than the circle, where you could have dozens of circles. You can have maybe, I don't know, 8s of these. Just being a little bit silly there. Polygons are better. This is probably going to be the one that serves a lot of complicated shapes the best. It's more expensive than the rectangle because there's more edges to compute. Compound objects need to be iterated through all the way for all the pieces. Lots of circles compounded are a lot cheaper than a lot of boxes compounded. And finally, there's the perfect pixel alpha mask bodies. These are potentially cheap. If it was a circle, it's going to be cheap, actually. But if it's got a convex or complex convoluted shape, there might be a lot of computation involved there, so just be careful with these. You need to pick the representation that best serves your game. You might find that the per pixel thing is actually better than having, like, say, 20 little circles to describe something. But prefer things on the efficient side of the chart as much as you can. Serve your gameplay. All right. Collision masks is another thing that you can use to regain performance, especially in a case like this. I've got these two jars, a white jar with white marbles and a green jar with green marbles. Now, the funny thing about this is they're pretty close together, and it might be hard for the engine to actually understand that the white marbles have no way of getting in the green jar and vice versa. So you can help the engine out. This is what the engine sees. It's like, for every one of those green marbles and every one of those white marbles, are they hitting? So just imagine how many comparisons that is. Putting the jar back again. Now, if you use a collision mask, give the white marbles mask 1 and the green marbles mask 2, you're going to get a whole ton of performance back. This is an order n squared problem. And so by cutting the number of comparisons in half, well, do the math. It's a lot of computation that you can get back just through this simple expedience. All right. Norman introduced force fields very nicely in the previous one, so I'm not going to belabor what all the different force fields are and their fields and things like that. But I am going to point out that they're building blocks. Use them together, and use actions to fade in and out. I have a big, nasty particle system here, and what I've done is just made a whole bunch of force fields throughout the center of the screen, and I'm just using an action to modulate the strength of each force field so that they smoothly segue one into the other. That's a lot nicer than just turning them on or off. Well, I love playing with these things endlessly. Had to throw that slide in. Now, here's another example. of how force fields can help you out in reducing game logic and simplifying updates, similarly to the way that the actions or the window into the engine. Force fields are another thing that you can use to replace game logic. So you can kind of tell without me even telling you what kind of a game this one is going to be, but let's just see what it looks like for a second. You can see the little guys are following my mouse cursor around, and they're doing their darndest not to run into those green planet things. I guess my spaceships are nearly as big as a planet. That's kind of amazing. It's hypnotic. Okay, I think I can stop staring at that now. All right. Ooh, wait, that's the big reveal. Let's go back to the picture of the movie again, or maybe not. Before I show you that next slide, what I want to tell you is using Xcode, I made that level. So I used an idea of, that I like to call prefabs, like prefabricated objects, to make a little scene graph with the spaceship's picture and a force field right underneath it. I gave the force field on the spaceship a negative strength, so they push each other apart. I gave the planet a child, which is a force field, with a negative strength, so that it pushes the little spaceships away. I made the planets not dynamic, and I made the spaceships dynamic. Okay, now we can look at that code. All right, so this is the whole entire of that game, aside from the bit that I built in Xcode. It's next to nothing, and you're getting the same sort of behavior that you see in classic RTSs like StarCraft or whatever. So what it's doing from top to bottom is just the target is where I tapped the screen. Well, you know what the ship's position is. I'm calculating, and I don't want to divide by 0, so I'm checking for that little minimum length. I'm getting the velocity from the physics body. I'm finding out what direction the velocity is in. Little arc tangent gives me an angle to slap on Z rotation. I'm taking the position difference of where I want to go from where I am, subtracting the velocity, multiplying it by a magic number, which I arrived at by iterating, and then I'm just applying an impulse using that calculated magic number. And you basically get what looks like artificial intelligence for having done nothing at all. Now, if you want to learn more about that stuff, you can search the internet for Boids. There's a wonderful body of work around these kinds of techniques. Now, just like physics debug drawing can give you insight into what's going on, here's, the wizard behind the curtain. I've turned on the field debug drawing. You can see the fields around the ships, the fields around the planets, and how they interact. And I don't know, it's a crazy amount of fun for 10 minutes of coding. So you all go out and make lots of cool spaceship games for me to download and play. I don't want to let that slide go away because I'll just watch it forever. Okay, so physics. Choose, I don't know which way I'm supposed to gesture. I had sheep down at that side of the screen. Choose the cheapest one that's going to best serve your game. Use the expensive ones judiciously to serve your gameplay. Separate your groups with masks so the engine knows what your intent is, because that's the only way that it can read your mind. Fields replace update logic. Use a little creative thinking, imagination. And the debug drawing is going to give you all kinds of insight into what the engine is doing for you behind the scenes. So, my next topic, shapes. I have a little refresher here on the difference between bitmap art and vector art. Anyone care to guess which is the vector art? Now, there's a cost hierarchy of shapes, just like there's a cost hierarchy of physics. You know what I'm going to say there? Choose the one best serves your game. These guys, in particular squares and rectangles, are really cheap. I'm going to say that sprites are way, way, way off the cheap scale beyond these guys, but not that far off. You can use these things a lot where it's appropriate. These are just a bit more expensive. You can use them a lot. These have had a ton of love put into them in this iteration of spritekit. And you can draw little mini maps and compass roses, all kinds of things like that with vectors that in previous iterations of spritekit you might have had them in the judicious column. Now they're in the delicious column. All right, stroked curves. Now I wish I could have a hockey stick to show you the cost here. These things look really great, and use a few of them and you're not going to really hit your performance at all. Use a bunch, you might get a call from mom. Finally, filling them in costs even more. So I just put a little bracket there so you know which is the cheap half and which is the expensive half. Use the thing that's appropriate to your game. Just because I can't stop myself, I made a fractal space pulling curve thing with tens of thousands of points in it, just to kind of say, hey, they're cheap, use them. All right, effect nodes. Use effect nodes when you want to have a subtree of sprites or whatever that are all going to together have some kind of effect applied to them, such as tinting or blurring. They have to be drawn off screen and then brought back to the frame buffer for viewing. So there's a cost. You can get really powerful core image support. You can run very sophisticated filters and all kinds of amazing things, but it's expensive. Use them when you need to. Shaders are an awesome option. Whenever you don't need to have things composited off screen particularly, and you can just go ahead and draw, shaders will save your performance bacon. If you want to just tint everything green, that's a really simple shader. You can just bypass, the whole processing stack, just go right out to the hardware. So learn about that. And should rasterize just gives us a hint about what can be cached and will hang around for a while and what needs to be recomposited every screen. If you've got things that are going to be static for a while, for example, maybe you've got some kind of a HUD display that only updates once every 10 seconds, but you want to have, N cool glows and blurs and radial distorts and all kinds of things going on, raster it out. There's a couple of cool things that you can do here. You can create a texture from a node and just specify the node, ask the view to raster it for you, and now you've got a texture. Just slap that up. It's going to cost almost nothing. If you have a CI filter, there's the other variant right there. All right, so that's what I have to say about effects. Now, for lighting. We had some good introduction from Norman in the last section about lighting, so I'm going to talk about the performance costs. So the first thing that you need to know is that, well, we're going to compute the lighting per pixel. So the cost is therefore proportional to the amount of lit pixels. You can optimize that with bit masks. If you say some things aren't going to be lit, then you're not going to pay that cost. So that's what that's all about. Ambient light is free. You can have 8 lights per sprite. Now, you're going to pay for, 8 times the processing per pixel per sprite. So weigh if you want to do that. And keep the cost down with the bit masks. Normal maps are cheap. The shader just eats those up, so stick normal maps on. They look great. Remember to share them. Shadows are cost proportional to the number of lights. It's pretty much constant. So if you turn on 1 shadow, that's going to cost you 1. 2 shadows, it's going to cost you 2. So keep the number of those things down. You potentially have to shadow the whole entire screen. So they look really great. They're going to add a lot of impact and awesome. Use them. Don't abuse them. All right. So we talked about drawing performance, understand what controls batching and draw order, and learn about the tools to get insight into what's going on. Actions and constraints are your window into the spritekit engine. We improve the efficiency all the time. The more you use actions, the more you're going to get performance back over time as we iterate the frameworks. Physics, understand the cost hierarchy. Choose appropriately to serve your gameplay. Same with shapes. Effects, understand the cost. Use them wisely. And lighting is a cheap and easy way to extra awesome. And I'd like you all to make your games as awesome as possible. All right. So today, we talked about structuring your games for scalability, understanding how to set up scene graphs and scene graph snippets so that you can put things together in a data-driven way. And we talked a whole bunch about performance. For more information, I encourage you to contact Alan Schaefer and Philip Iliescu, who are our games evangelists. The spritekit programming guide, recently refreshed, has a ton of interesting information in it. And of course, there's always the forums. And tomorrow, I would love if you could all come and visit us in the labs and talk about what you've got going on and, say hi. And with that, thanks very much, and I'll see you all later.